So thank you very much. It's a great honor to be giving these talks. I was instructed that these talks should be accessible for a scientifically literate audience, and I've taken that very seriously, so I apologize to any mathematicians who have come and have expected more detail. So let me start from the beginning. What is a number? So the ancient Greeks, their concept of a number was simply an integer. But they did have a second concept, which is closer to what we think of as a number, but was the notion of a ratio or a proportion. So we can think about numbers in this way as well, but there's something subtly different. And one thing that's different is that this way of thinking about numbers emphasizes a certain type of number, namely a ratio of one integer to another integer, or a proportion that corresponds to one integer to another. Okay. So we can define a rational number to be exactly a proportion of two integers, or in other words, just a ratio of two integers. And it was a big discovery by the Greeks, and particularly the Pythagorean school, when they discovered that not all proportions were rational. So Pythagoras' theorem tells us about the relation between sides of a right-angled triangle. And in particular, if you take a right-angled triangle in which two side lengths are the same, the ratio of the length of the hypotenuse to one of the sides is the square root of 2. And they famously proved that this was not a rational number. So this is an irrational number. And my talk is about explaining how mathematicians think about irrational numbers and how they influence the history of how we think about numbers more generally. So the Greeks had other problems that they tried to study that related to this notion. One example, we could take a circle and a square, both with the same diameter. And you could ask, suppose I take some finite number of circles and I take some finite number of squares. Is it possible to choose the circles and the squares so that the total area of all the circles is equal to the total area of all the squares? So what type of question is this really? So the area of a square, or rather the ratio of the area of a square to the area of a circle with the same diameter, is related to pi. And so a version of this question, said more in today's language, is pi a rational number? So not to give too much away, if you know something about pi, you probably know it's an irrational number. So the answer to this is no. But this is not a question that the Greeks really understood. They didn't know the answer to this question. They had some other related problems as well. There's the infamous problem of squaring the circle, which involves something related to this, but not directly related to this. But this is certainly all about the question of what is pi really? Okay. So how do mathematicians think about irrational numbers? I want to give you the first level way of thinking about it. And to explain that, let me remind you, as I'm sure you all know, of scientists, of Occam's razor. So Occam's razor is more or less the explanation that the simplest explanation is the best. There's no need for unnecessary hypotheses. And a formulation of that in terms of how mathematicians think about irrational numbers is the following. That if you have any number that comes up naturally in mathematics, for example, the square root of 2 from a right-angled triangle, or pi from a circle, or any other number, then one of two things happens. Either it's a very simple rational number, maybe it's an integer, or it's irrational. Right? You never have a natural problem that comes up in real life for which the answer is 173 divided by 1,026. That just doesn't happen. So, I mean, this is a very naive way of thinking, but it's a remarkably effective and usually correct way of understanding what's going on. So let's jump forward a few hundred years to the 18th century, when we start to get the first theoretical results. So here we're at first at the point where we actually have pictures of the actual mathematicians that are accurate. Here are three such mathematicians. This is Lambert, Legendre, and Lindemann. Well, I say we have accurate pictures. For many years, this middle picture was thought to be of the famous mathematician Legendre, until it was discovered it was actually a politician, Legendre, of the same name. And so there was a mad scramble to find an actual picture of him. And the best that we could come up with was the following contemporary caricature. You'd probably say, well, this looks much more like a mathematician. So Lambert's claim to fame was that he was the first person to prove in 1760, so several millennia after the Greeks, that pi was actually an irrational number. So I give just the first page of his paper for two reasons. The first is he really undersells his result. He just answered a question that's been open for 2,000 years, and he starts off by saying, we prove that pi is irrational. This will not surprise any geometer. Okay. I don't recommend you write your papers like that today. But the other reason is here is a clear enunciation of exactly this principle, this Occam's razor for irrational numbers, that Lambert says in print. So he literally says, if you take an infinite sum of rational numbers, then the answer is either going to be an integer or a very simple fraction, or it's going to be irrational. So, I mean, this sounds a very kind of basic thing, but it really is how mathematicians think. Okay, so he goes on in this paper to prove that pi is irrational. So what is pi? Right, so you can think about some decimal expansion. That, of course, doesn't capture any of it. And there's something a little bit strange, namely that when you give it a name, when you write down a symbol, somehow you can start to pretend that you understand what it is. This is my one Linnaeus joke, by the way. I mean, if you were told that the ratio of the circumference of a circle to its diameter was pi, I mean, you could ask, have you really learned anything about what that answer was? You've just told the answer is pi, which is almost a definition of what it is. If you came back later and found out that actually that ratio was 3, you would feel pretty cheated that someone didn't tell you pi was 3. And so it's sort of surprising that you have this concept that exists for 2,000 years before finally someone says that, oh, it's actually an irrational number. So of these three L's that I showed you from the previous page, so Lambert, my best of Swiss German pronunciation, proved that pi was irrational. Legendre in 1794 proved that pi squared was irrational. So that's a stronger claim. There are certain numbers that are irrational, but whose squares are rational. For example, the square root of 2. And finally, to some extent, 100 years later, Lindemann proved a stronger statement, not only pi squared, but pi cubed, pi 4, all these higher powers were irrational. In fact, he proved slightly more. And one way of understanding what he proved was he really showed that you couldn't write pi in any simpler way. So that was a final justification for thinking about it as a concept that was really a new number and deserved its own symbol. It was something that was separate from anything that had come before in terms of integers or rational numbers or even square roots and other constructions. Now, of course, that was a justification, but as I said, mathematicians for many centuries had, at least in their bones, known that this result was true. Okay. Let's move forward. So here is a picture of the famous mathematician Euler and a quite pretty picture of Basel. And so here we come to a problem known as the Basel problem. So mathematicians in the 17th and 18th century loved to challenge each other with various challenges. And one particularly famous problem was to work out a closed form for this sum. So here I'm just taking the sums of 1 of 1 squared, 2 squared, 3 squared, sum of all the inverse squares. So this was something the Bernoullis tried to solve it, but they failed. And perhaps Euler's first claim to fame was that he was able to crack this problem. Curiously enough, he first computed it numerically, which is not so easy. Then he recognized the number as pi squared on 6. And then he went on to give a proof. So this was, of course, considered a complete answer, even though in 1734, it was not known that pi squared was irrational. Right? So maybe this was also a rational number, but of course, Euler certainly suspected that it wasn't. And 60 years later, Lagrange proved that it was. Maybe just in passing, I wanted to make the remark, I think that we all know that science is not done in a vacuum. It's done as part of a kind of broader enterprise within society. And 1794 is an interesting time to be doing mathematics in Paris. It's kind of the peak of the reign of terror. In fact, in 1793, Lagrange lost all his money, various political reasons. And then he married a rich woman. And because of that, was able to continue. I mean, it's worth noting that a lot of science only gets done for reasons due to the rest of society. I make no comparison with today's political situation. All right. So in addition to understanding what the sums of the inverse squares were equal to, Euler also was able to compute the sums of the inverse 4th powers, the sums of the inverse 6th powers, the 8th powers, the 10th powers, the 12th powers, the 14th powers. There's a pattern. For every even number, he showed that the answer was the appropriate power of pi times a rational number. That naturally raises the question, what happens if I take the sum of the inverse cubes or the inverse 5th powers? Now, in general, you can take the sum of the inverse x powers for some real number x, and Euler studied that function. This was a function that later became known as the Riemann-Zeta function, which is certainly a very famous function in mathematics. But even just computing these numbers, the analog of the Basel problem for these odd powers, was something Euler certainly tried to do. And there's a naive guess when you look at what Euler did, the even powers, is you might look at the sum of the inverse cubes and you might say, well, my first guess is this should be a rational number times pi cubed. So that's the naive guess. So you can, and Euler did, compute this number, and then you compute the ratio with pi cubed. And what you find is you get something that doesn't look like a rational number. And so if you apply Occam's razor, your prediction is that zeta 3 is not pi cubed times a rational number. Right, so that's how mathematicians think. Great. So what's the answer? In fact, this is still an open problem. So 300 years after Euler tried to compute this, we don't know if it's a rational multiple of pi cubed, although of course we do. It's not. So let's go back a little bit and say, what exactly is pi? So again, in this concept of ratios of the Greeks, pi is defined to be the ratio of the circumference of a circle to its diameter. Now, again, if you know 3 things about pi, this would be 1. Maybe you know it's irrational, and maybe you know it has something to do with the area of a circle. But that, of course, can't be the definition. We can't have 2 different definitions. It's a theorem. So a theorem is the area of a circle. Its radius r is pi r squared. So if you were to prove this fact, well, if you were to prove this fact in high school geometry, you would probably do it something like this. You take your pizza, you cut it up into very thin strips, and then you rearrange it so it looks a little like a rectangle. And then as your slices of pizza become thinner and thinner, your rectangle becomes closer and closer, almost rectangle, becomes closer and closer to a rectangle whose side lengths are the radius and half the circumference, which would be pi r. And then the area of that rectangle is pi r squared. And this is more or less how someone like Archimedes would have argued, but it's perhaps not the most entirely rigorous way of understanding areas and arc length. A more rigorous basis for that, at least in terms of modern mathematics, is to think about calculus. So how do we think about this in terms of calculus? So there are formulas. If you can write down a formula for a circle, then you can write down a way of computing its area, and then you'll end up with this integral on the left-hand side. You can also have a formula for the arc length, and then you end up with a formula that's this integral on the right-hand side. And so the theorem is that these two integrals are equal to each other. So one way to try to do that is maybe just to compute the left-hand side and get pi, and to compute the right-hand side and get pi, right? They're the same. But in order to integrate these, you have to use various complicated things. And you might ask, is there really a direct proof of showing these integrals are the same without computing first that they're equal to pi? Just by using elementary calculus. And so the problem is, I mean, these expressions aren't really things that you can integrate directly. But it turns out that if you take their difference, perhaps surprisingly, the difference of these two functions does have a nice antiderivative. Write this integral as a simple form. And so then when you can compute this, you see that this right-hand side is the difference of this function at 1 and minus 1, so it's just equal to 0. So this gives you a proof just by using simple calculus, not using anything about geometry, not using anything fancy, that tells you that these two integrals are the same number. Okay. So you can teach a monkey how to differentiate, a smart monkey, but integration is much harder. Right? Differentiation is really just a process by a set of rules. Integration is often something that you really have to use tricks to do. And this is sort of really the case here. I gave you a proof that the area and the circumference were related by some trick in which I subtracted things and then integrated it directly. But it's not so clear if I was lucky that that happened or whether I can do this more generally. And so this starts to lead us to a second way of thinking about irrational numbers that's going to be a bit more sophisticated than simply Occam's razor. So I'm going to start out by formulating a conjecture that does seem very vague, but can be made very precise. So the conjecture is that if you ever have an equality between integrals, like we had on the last page, you can always prove it in this way, by a sequence of maybe chopping up the integral, maybe using various substitutions, by some sequence of manipulations that are essentially just elementary to show that you get an equality. All right, you have to kind of set this up precisely by what you mean, what type of integrals you're allowing, certainly including the ones on the previous page, but it's something that you can make precise. So another way or another variant of thinking about what this conjecture means would be as follows. If you have an integral that's equal to pi, well, the first integral was involving the area of a circle, that your other integral that's equal to pi, it somehow has to involve a circle in some way. Well, I mean, I'm descending into very vague descriptions, but there has to be some hidden circle in the expression that you're integrating, right? By some series of substitutions and breaking it up, you have to see a circle going on in that. And if you just turn this around the opposite way, what you deduce that is if your integral doesn't involve a circle, then the value has to be independent of pi. So this is sounding just as vague as Occam's razor, which is to say, well, if it clearly involves pi, it should. If it doesn't, it shouldn't. But what's different about this conjecture is you can make it more precise to the extent that you can actually determine this question about whether the integral involves a circle or not. So it gives you not just a conception, but it gives you an algorithm for making predictions. In fact, this conjecture is really a combination of two very important conjectures in mathematics. Here we have William Hodge and Alexander Grothendieck. And so these two conjectures, well, first, let me kind of say exactly, well, not exactly, a little bit more. We have certain integrals that we're allowing. So integrals of polynomials, integrals of various things involving square roots. We have a precise things that we're allowed to integrate. And the things we evaluate in this case, they have a certain name. They're called periods. So these periods, they certainly include all integers, all rational numbers, all square roots, all things like pi, all the numbers that you recognize usually at this point. And then these two conjectures, the Grothendieck period conjecture and the Hodge conjecture, they predict that any equality between these periods, any equality between two integrals, arises from some geometric reason. Again, geometric is in scare quotes, but I hope my example with the radius of the circumference of the circle and the area gives some indication of what I mean. So in fact, the Hodge conjecture is one of the most famous problems in mathematics. At the turn of the century, the Clay Foundation listed 7 millennium problems. If you solve one of these problems, you get $1 million. And one of these problems is the Hodge conjecture. And I invite you to go and look at Wikipedia tonight, what the Hodge conjecture is, and then you will have no idea what it's saying. And instead, I would hope you would think that what I'm talking about here, the fact that you can go from some equality of numbers and to actually have an algorithm for understanding what's going on in terms of geometry, as really some clue as to what this important conjecture in mathematics is really about. Okay, so let's go back to a problem that Euler thought about. So we take z to 3, which, to remind you, is just the sum of the inverse cubes. And as I said, the naive prediction, just from Euler's result about squares and 4 powers and 6 powers, would be that it's a rational multiple of pi cubed. But then if you compute it and see, it doesn't look like it's a rational multiple. So by Occam's razor, you predict it's not. But if you use Grothendieck's period conjecture, then you can make this prediction before doing any computation. And it really tells you in advance that z to 3 is a number, just like pi before it is something that has nothing to do with any number that has come before. It's independent of any rational number. There are no square roots. It has nothing to do with pi. It's really a new number. And so the question of evaluating, like, what is the sum? I mean, the only answer of what is the sum is it's z to 3. It is what it is. And you can't somehow simplify pi any more than pi, but there can be new numbers, which even when you have pi, have nothing to do with that. And Grothendieck's period conjecture really explains all these numbers and where they come from and what relationships they have or don't have in a way that's satisfactory. And as I sort of suggested, one nice thing about this conjecture is, on the one hand, you can just apply it in a particular case to make a prediction. And it also has explanatory power, right? It explains why things should have relations and why things don't have relations for some geometric reason. So it both explains what's going on and allows you to make predictions. So if we were doing science, we'd be done now. Right? We'd have the answer. This explains everything, makes all the predictions. But we're mathematicians, we're not scientists. So, I don't know if that's politically correct or not. The downside is we have no idea how to prove this conjecture. Right? So even though it explains all the phenomena, it makes all the predictions, we are completely hopeless in understanding or even starting to try to prove why Grothendieck's period conjecture might be true. And as I said, this particular problem of if zeta 3 is a rational multiple of pi cubed or not, this is still a totally open. Okay. So I'd like to just put Grothendieck's period conjecture in action in a particular case. So I'd like to consider these three sums. So here, what do we have? The first one is just the Basel problem. It's the sum of the inverse squares, every single square, 1, 2, 3, 4, 5, etc. The second sum is what happens when you start at 1 and you take every second integer, every odd integer, 1, 3, 5, 7, 9, dot, dot. And the third sum is what happens if you take every third integer, 1, 4, 7, 10, dot, dot. So maybe you find a way of computing these numbers. These are correct approximations. You can certainly look at these. These don't look rational to me. Great. So by Occam's razor, we certainly predict that they're all irrational. But you could ask, what does Grothendieck's period conjecture say about these three sums? Well, wasn't Grothendieck's period conjecture about integrals? Yes, but it's not so difficult to write these sums in terms of integrals. Here is just a kind of simple way. It's not so important just to say that we are in the world in which, just by writing them, these things on the right are just definite integrals. We're in the world in which Grothendieck's period conjecture applies. So what predictions does it make? Well, it predicts that the first sum is irrational. That's great. What about the second sum? It also predicts that it's an irrational number as well. But even more, it actually predicts that there should be a relation between the second sum and the first sum. That there should be some rational relationship between them, right? It both predicts when there is a relationship and when there isn't. But it predicts that the third sum is, once again, a completely different number that is neither rational, nor does it have anything to do with the first two sums. Kind of superficially, of course, they all look kind of similar, but when you convert it into a problem in geometry, you see that the first two are very closely related, but the third is something completely different. Okay. Well, as shown by Euler, the first sum is pi squared on 6. And we've known since 1794 that this is irrational. The second sum, pi squared on 8. And that is indeed a rational multiple of the first sum, 3/4 times the first sum. And it's also still irrational, still by Lagrange's theorem. And so what about the third sum? So in the context of this problem, of understanding these type of sums, there was, of course, the theorem of Lagrange, and then there was no progress for 230 years until last year with my collaborators. We verified exactly this prediction that the Grothendieck period conjecture gave us, that this third number, on the one hand, it's irrational, but it's also nothing to do with pi squared. It's not pi squared times any irrational number. This is kind of the framework of time it takes mathematicians to prove things. I should say, if you take the next one, where you take a sum 1 plus 5 plus 9, we're once more into the world of things being totally open. I hope it won't take another 200 years to solve. Okay. Here, by the way, is a picture of my collaborators. Okay. So I don't just want to talk about history. I also want to give you at least just a taste of what is the mathematics that's going on. So I want to say something about how to prove a number is irrational. And I really want to prove the following claim. If you take any mathematics away from this lecture, I want it to be the next 3 lines. So now's the time to pay attention. And so what I want to prove is, I'm not going to prove that pi is irrational, but I'm going to prove that if it was a rational number, then it has to at least be pretty complicated, that b has to have at least 3 digits. Okay. And so the proof, it'll be 2 lines. And so in order to prove it, we have to be able to at least do some computations with pi. And we're going to use the fact implicitly that pi is pretty close to 22 on 7. Okay, so here's the fact we're going to use. So if pi is pretty close to 22 on 7, 7 pi is pretty close to 22. How close is it? Well, pi is not equal to 22 on 7. Check that by computation. And how small is this difference? If you can compute pi, if you have a calculator out, you could do it right now. You get something 0.0088, something less than 100th. All right. So as long as you believe me in this computation, in the next line, we're going to prove that pi is not a simple rational number. And so what's the proof? So if pi was equal to a on b, well, 7 pi would be 7a on b. And then I want to subtract 22 from that. So we're in the world of adding and subtracting fractions. You're scientifically literate. If this was a public audience, you'd have bad flashbacks of adding fractions, but you're okay with adding fractions. How do you add fractions? You put them under a common denominator. So I take this difference, and it becomes 7a minus 22b divided by b. And so what's the key point? So we know this number is not 0 because we computed it numerically. But if we look at this numerator, 7a minus 22b, if a is an integer and b is an integer, this numerator is an integer. And so now we use what's sometimes called the fundamental theorem of transcendental number theory, which is that the smallest non-zero integer is at least 1. So the numerator is at least 1. Right, so that means if pi was equal to a on b, how close, how small can this be? It has to be at least 1 on b. But we just computed it was at most 1 on 100. And so if you put these two facts together, that shows that b is at least 100. So we prove that. Now you could say, well, I could just, there are only many cases to check. I could just even do this numerically, and you could. But it's this general idea that you can start to try to apply to show that pi is not equal to a on b, where b has 5 digits, or 8 digits, or 10 digits, or more and more, as long as you find, I mean, we've done a bit of magic here by producing this number 22 on 7. So for example, let's prove that if pi was equal to a on b, that actually b has at least 10 digits. I mean, now, once you know this, then by Occam's razor, I mean, there's no way it's going to be a rational number. All right, so I have to do the same thing. I mean, the argument's not going to be any different. I have to kind of produce some pair of integers such that when I take a times pi minus b, it's small. But I want it to be smaller, that not just than a 1 on 100, but maybe smaller than 1 on a billion. So here we go. Okay, depends what kind of calculator you have. But if you know how to compute pi, computing this is a triviality. And what you see is it's bigger than 0. And you take, pi is not that rational number, but it's less than the billionth. And so the same argument shows that b has to be at least a billion. And so now you get a hint of how you might prove that something is irrational. You just have to produce whatever it is that you're coming up with here, up 22 on 7, whatever the sequence of numbers is, right? I mean, the property of 22 on 7 was that 22 on 7 is pretty close to pi. Okay, so you might say, well, I know how to write down a rational number that's close to pi. I can just form its decimal expansion, 3.1415926353, and let's just stop there. If I stop, it's a rational number. It's pretty close to pi. Why can't I use that? All right, so let's see what happened if we try to do that. So here it is. Yeah, it's pretty close. But it was important in these previous approximations. It was not just that pi had to be close to 2217, something stronger was true. So I want to explain why the naive construction of these numbers is not good enough. I mean, let me just remind you what that previous approximation was. So if you take the number that pi is actually close to and see how close it actually is, pi minus this fractal number is really small. It's 10 to the minus 20, right? But in this case here, these two rational numbers are about as complicated, like they have roughly the same size numerator and denominator. But this one on the second line is a much better approximation. And in fact, if you take this last approximation and try to convert it to a form that we actually used, you would only get that this difference is not 10 to the minus 9, it's 0.89. And so what does this approximation tell you about pi? It tells you it's not an integer. Okay, well, we probably knew already pi wasn't 3. Right? So it's not just about finding rational approximations to pi. It's about finding really good rational approximations to pi. And in fact, a theorem of Dirichlet tells you that if a number is irrational, you can find these really good approximations. And if you can find these really good approximations, then you can prove that pi is a number is irrational. So it's the whole game is about producing some mysterious sequence of numbers that somehow are giving approximations to pi, right? And those numbers don't necessarily turn up in a natural way. I mean, 2217 we know, maybe probably only if you're a mathematician, you might know 355 on 113. That's the next one that's better than 2217. I'd be surprised if anyone knew this one. And it's not clear that there's an infinite sequence of such things. And so that kind of becomes the game or the problem of where do you find these things? Where do they come from? And the sad news is that producing these things is often just a complete mystery, right? Which is why we're so bad at proving numbers are irrational. So trying to prove that pi is irrational is not something I can really explain in terms of giving any details, but I actually can say something about a simpler number, which is the golden ratio. Now, you can actually work out what the golden ratio is equal to and use that to give a simple proof, but I want to give a proof that gives more the flavor of how modern approaches to studying irrationality of other numbers work. Okay, so what is the golden ratio? There's a few different ways in which it comes up in mathematics. Relevant for us is if you take the following sequence of numbers: 1, 1, 2, 3, 5, 8. These might be familiar. The way the sequence is defined is each term is the sum of the two previous terms. Right? 8 is equal to 3 plus 5. 13 is 5 plus 8. This is the Fibonacci sequence. And if you take the ratio of consecutive terms of the Fibonacci sequence, they end up converging to the golden ratio. Right? If I take 8 divided by 5, that's 1.6. As you go along, these ratios are getting closer and closer to this number, which is the golden ratio. So to prove the golden ratio was irrational, to prove that anything was irrational, what we wanted to show was that if it was equal to A on B, that first B had to have at least 3 digits, and then it has to have at least 10 digits, and then it has at least 20 digits. And we want to do that for every single number of digits, and then that will be a contradiction. I mean, if the golden ratio was rational, its denominator has some number of digits. We don't know in advance what that might be. And so all we need to do is kind of find these better and better approximations. So with pi, we had 2217, and then we had some other mysterious numbers that were unfamiliar. But in the case of the golden ratio, we're even defining it as the ratios of these consecutive Fibonacci numbers. And so that actually gives us possible numbers that could approximate this golden ratio. For example, 89 and 144. So of course, 144 divided by 89 should be close to the golden ratio. But when we think about it in this way, which is what we really need to do, we see this is between 0 and something close to 1 on 200. So just like with proving that pi, if it was a on b, it had to have at least 3 digits. Already, just putting in these numbers, 89 and 144, tells us that if the golden ratio was the form a on b, that b would have to be at least 200. But unlike the case of pi, in this case, we can write down an infinite sequence of these pairs which give us good approximations. Namely, we take each Fibonacci number and the consecutive Fibonacci. Right, so to prove it's irrational, what we want to show, we exactly want to take these quantities of some integer times the golden ratio minus some other integer, and we want to show we can make that smaller and smaller and smaller. We also don't want it to be 0. Of course, if it was 0, then it would be rational. And so here we have actually a handle on actual numbers that could potentially work, namely these Fibonacci numbers. So we have to prove some fact about these Fibonacci numbers and their ratios. Okay. This is going to be my most actually doing math slide, but I'll tail off after this slide. So here we go. Here are these numbers. We want to show that these numbers, so this is a Fibonacci number times the previous Fibonacci number on the golden ratio. We want these numbers to be getting smaller and smaller and smaller. If they're getting smaller and smaller and smaller, and they're all non-zero, that will prove that the golden ratio is irrational. Right, so phi is about 1.6. So this first number is 1 minus 1.6, which is minus 0.6. The second number is maybe 0.4. I'm not going to try to compute the third number. Okay. So one thing we know about the golden ratio is that it satisfies this quadratic equation. Its square is equal to 1 plus the golden ratio. And so actually using that, we can start to simplify these expressions here that we want to show as small. So if I take 1 plus phi and I square it, expand that out, 1 plus phi squared minus 2 phi, and I simplify it, I get 2 minus phi. And if I ever have a phi squared, I can always simplify it just by using the equation. If I take 1 minus phi cubed, and I multiply it out and I simplify it, I get 3 minus 2 times phi. If I take 1 minus phi to the 4 and take its power, I get 5 minus 3 times phi. And so what you can prove by a simple mathematical induction is these numbers that we want to show are getting smaller and smaller. In fact, they're just given by the powers of 1 minus phi. So 1 minus phi is minus 0.6. Particular, it's less than 1. And so its powers are getting smaller and smaller. So the first number is sort of minus 0.6. The second one is that square. Its cube, its fourth power. These things are getting smaller and smaller. And they're all non-zero. And so these quantities on the top are getting smaller and smaller. And so we're getting better and better approximations. And each time we prove that if phi is a on b, phi has to have more and more digits. And that's a contradiction, because if it was a on b, at one point we couldn't do any better. So this is really a proof that the golden ratio is irrational in the style that that we try to think about irrationality today, sort of finding these good approximations. Now, of course, there's something special about this case in that the golden ratio itself was even defined by taking these sequence of rational approximations, whereas pi is not defined that way. Pi is defined in terms of a circle, and it's not clear that these numbers have a special form. And if you look at them, 22 on 7, 355 over 113, they don't clearly form part of some sequence that you can write. So even though this is the approach, it's usually a complete mystery how to find the right sequence, how to get a handle on a good enough sequence. Okay. So there are lots of numbers that turn up in mathematics, and the Grothendieck periodic conjecture gives you an explanation that most of them have nothing to do with each other and that they're all these completely new numbers. But after this progress that culminated in Lindemann's proof about pi that was transcendental in the late 19th century, there was really a bit of a gap between any progress on any of the numbers that I've talked about today. But then there was a very surprising breakthrough in 1978 when Roger Uppary came up with a following sequence of numbers. In fact, there are two sequences. So you should think about this as something like the Fibonacci sequence. I'll give you a definition in a moment. That was one of the sequences. This was another of the sequences. Well, that's not quite a sequence of integers, but never mind. And this sequence, well, just like the Fibonacci numbers was related to the golden ratio, this sequence was related to zeta 3, this mysterious sum of the inverse cubes. And so what do I mean? Well, let's just, for example, choose, I think, the fifth term in the sequence. If you take those numbers, so here we see that it's 33,001, and we also see this 288 and this number here. By cooking up something from these two sequences together, we get a remarkably good approximation to the sum of the inverse cubes, this zeta 3, this number, this mysterious number that Euler had studied that we knew nothing about. So already here I've given a proof that if zeta 3 was a rational number, its denominator would have to have at least 5 digits. And so what happens is, just like with the Fibonacci numbers, as you take more and more terms in this sequence, you get better and better approximations to this number. These things are getting smaller and smaller, and you prove that zeta 3 is an irrational number. So this was a kind of a shocking thing. What is the definition of this sequence? Just to show that it looks a little bit like the Fibonacci sequence. Right? There's a relationship from one term between the previous two terms. But I mean, if you look at this, it's like, where is this coming from? I mean, it didn't help, in fact, that when Uppary gave a kind of infamous talk on this in 1978, that he started making random assertions. He put sums, which had all sorts of things with terms that involved infinity. People didn't believe him at all. Someone asked, where do these formulas come from? He said, I grow them in my garden. It was a fairly infamous talk in which people were throwing paper planes and laughing at him, and there was only one person in the audience took him seriously enough to check it. And so after Uppary's proof, people thought the floodgates have finally opened. We can try to understand what Uppary is doing. We have a new approach to proving irrationality. And what they did was that they tried to understand where Uppary's sequence was coming from, like what are these numbers, tried to produce new such sequences that would give you the irrationality of other numbers, maybe zeta 5, maybe zeta 3 divided by pi cubed, all sorts of other things that we had guessed for many years would be irrational. And the long and short of it is that despite a kind of huge amount of research coming out of it, no one could ever apply Uppary's result to prove that any other number was irrational. I mean, it's sort of amazing that there's lots of happy accidents that occur in this particular example that make reproducing it a little bit like trying to reproduce magic. So what is going on? I mean, as I've tried to emphasize, all these methods, right, even showing that pi is not too close to that the denominator is big, they all involve finding these sequences a, n, and bn, of these integers, such that when I take like integer times pi minus another integer, that's small, and finding a sequence of these things are getting smaller and smaller and smaller. That's the whole kind of engine that is producing irrationality. And then the mystery is, how do I find those sequences? And as I said before, if you just cut off the decimal expansion, that's not good enough, right? So a kind of weaker condition is simply saying, dividing both sides by n, is simply saying, oh, a sequence of rational numbers that are getting closer and closer to pi. Or closer. That's never good enough, because you can just always produce that in the easy way. Even if you take a third, 0.33333, of course you can just chop that off, and that's a rational number that's getting closer and closer to a third. You're not going to prove in this way that a third is irrational, because it's not irrational. And so I think the summary of what we did in our research was not to produce a new way of finding these magical sequences that Uppsala had found, because people have tried that for 45 years and failed. What we understood is that you could possibly get a rationality. Well, the second one is clearly not good enough. The first one is good enough, but that there was an intermediate condition. There was situations where you could find a sequence which satisfied the second one, but not the first one, but had some other intermediate properties, and that those properties were still good enough to allow you to deduce the number was irrational, even though the naive argument using common denominators is not good enough. That was kind of a basic idea behind our paper. I mean, it's also 300 pages, so there's some more ideas, but that's kind of the breakthrough we made was not to kind of find the sequences that people had searched for, but to say that you don't need that much. You can do with something weaker. And that weaker condition, it is then easier to find such sequences. And that allowed us to kind of make progress on this question that had been open since 1794. So thanks for listening.
Thank you very much. Give us an idea of the mystery of number theory. So I'm really fascinated. We have time for some small questions. We have also a panel discussion afterwards, but some small questions we can now ask. Stan.
Well, isn't there a product which gives pi over 4, a product of integers?
Yeah, I mean, so there are many. So, I mean, Leibniz, maybe even mathematicians going back to India hundreds of years before that, produced lots of expressions that give you pi. And so there are many things that give you pi, and that they give you a sequence of rational approximations. But the point is that what will happen is that those sequences, I mean, it's not good enough for them to be getting closer and closer to pi. They have to be getting closer and closer to pi very, very quickly. And typically any such sequence is not going to do the job. And in particular, even finding, I mean, we knew that pi was irrational in 1760, but even finding using this method a proof that pi is irrational is still very, very tricky.
Okay. More questions about Riemann function, pi. Wait, you get the microphone.
Yeah, I'm going to throw it here.
Yes, give it.
I will, yeah.
Yeah, question over there? Okay.
So you have an appointment, yes?
I mean, this is a picture from our paper. So the part of the proof uses some fact here. I think it would probably take me a little bit too long to explain what exactly is going on.
You will only give us the beauty of the picture.
No, well, okay. I mean, I'll give you a very. It's one way of thinking of what Uppsala was doing, was working in a situation where you had pictures like that, but you had to only work with circles. And we work in a context in which you can use objects that are not circles, that when you have points in the way, allow you to push yourself a bit further. I'm not sure if that made sense or not.
So that was in your garden, this picture.
Yeah. This was...
Some more questions. We have a panel discussion. We have a panel discussion also for more. Can I have a stupid question? Why is pi gets the symbol pi? Is there a story behind?
I mean, I think this only happened in the early 18th century. I mean, it was just before described by its definition, which was this ratio, and then maybe some English mathematician used it. I mean, basically, Euler started using it, and then, I mean, if Euler does it, it's good enough for the rest of us.
Okay. More question like that? No, but then I can give you, we have time to give you the present. Is something related to Celsius. so that you have a chance to measure the temperature